Hello there, and welcome to the deep Somna. I'm so glad you're here. Maybe the day has been long, or maybe you're simply the kind of person who finds peace in thinking about distant worlds and quiet cosmic rhythms as sleep draws near. Either way, this journey is made for you. There's nothing you need to do now except let yourself settle, let your breathing slow, your muscles soften, and imagine that gravity itself has grown gentler, as if you're beginning to drift upward through invisible currents of space. Tonight, we're going to float gently through the solar system, not rushing from planet to planet, but drifting in slow arcs through magnetic fields and ancient ice, past storms that have raged for centuries and moons that hide secret oceans. A story told not in equations, but in the quiet strangeness of tilted worlds, vanishing rings, and light that takes minutes to cross the void. And before we begin, if these quiet wanderings help you unwind at the end of your day, feel free to like and subscribe. It helps others find their way here too, one restful soul at a time. Now, let's begin our drift. The sun sits at the center of everything we know in this small corner of the galaxy, a sphere of hydrogen and helium so massive that it contains more than 99% of all the matter in the solar system. Everything else, all 8 planets, their moons, the asteroid belt, the distant comets, the dust, the ice, amounts to less than a fraction of a single percent. And yet the sun is not violent in its dominance. It simply is. It burns steadily, fusing hydrogen into helium in its core at temperatures beyond 15 million degrees, releasing light and warmth that flood outward in all directions. This energy doesn't rush. Photons created deep inside take hundreds of thousands of years to work their way to the surface, bouncing endlessly through dense layers of plasma. Only when they finally escape do they cross the remaining distance to Earth in just over 8 minutes, arriving as the sunlight that warms your skin and brightens the sky. But the sun is not a silent sphere. Though we cannot hear it, the sun hums with sound. Pressure waves ripple through its blazing layers, created by rising and falling currents of plasma. These oscillations generate ultra-low frequency vibrations, far below the range of human hearing, but scientists can study them through a technique called heliosysmology. Its internal structure, much like geologists, use seismic waves to explore Earth's interior. The sun's hidden rhythms reveal magnetic activity, convection patterns, and the dynamics of fusion deep within. It is always vibrating, always singing quietly to itself in frequencies we cannot perceive. And every second, the sun loses mass. More than 4 million tons of itself, converted into pure energy through the alchemy of nuclear fusion. It's a minuscule loss compared to the sun's total mass, but over billions of years, it adds up. The sun is slowly giving itself away, atom by atom, to keep the solar system alive. Eventually, in about 5 billion years, the hydrogen fuel in its core will run out. The sun will swell into a red giant, expanding outward until it engulfs the inner planets. Then it will shed its outer layers in a glowing shell of gas, leaving behind only a dense core, a white dwarf made mostly of carbon and oxygen. This ember will no longer generate energy, but will cool slowly over trillions of years, fading into darkness. For now, though, the sun burns steadily, a patient star in the prime of its life. The sun's outer atmosphere holds a mystery that has puzzled scientists for decades. The visible surface, called the photosphere, has a temperature of about 5,500 degrees. But the outer atmosphere, the corona, reaches temperatures exceeding 1 million degrees. This seems backwards. Why would the outer layers be hotter than the source of heat beneath them? One theory suggests that magnetic waves from deep within the sun transfer energy upward, heating the corona from below. Another possibility involves tiny solar explosions called nanoflares, which might release energy in sudden bursts. Either way, the corona glows with searing, mysterious heat, a luminous halo around the sun visible only during total solar eclipses. The sun also has a heartbeat of sorts. Roughly every 11 Earth years, the sun's magnetic field flips completely. The north and south magnetic poles trade places in a process tied to the sun's internal dynamics. This solar magnetic cycle affects everything from sunspots to solar flares and coronal mass ejections. At the peak of the cycle, called solar maximum, the sun becomes more active, with intense radiation and magnetic storms. As the cycle wanes, activity decreases until it reaches solar minimum. These cycles ripple outward, influencing Earth's upper atmosphere, satellites, and even the auroras that dance near the poles. The sun's magnetism is not fixed. It pulses and flows, a breathing magnetic presence at the heart of the solar system. Sunspots mark the sun's surface like temporary scars. These are regions where intense magnetic activity suppresses the flow of heat, making them cooler than their surroundings, though still blazingly hot by any human measure. They can grow larger than Earth and often appear in pairs or clusters, following the 11-year solar cycle. Despite their name, sunspots are not dark in any absolute sense. They only appear darker by contrast, still glowing at thousands of degrees. They reveal the sun's restless interior, where magnetic fields twist and churn beneath the surface. In 2018, a spacecraft called the Parker Solar Probe began a series of increasingly close passes through the sun's outer atmosphere. Protected by a carbon composite heat shield, it endures temperatures exceeding 1,000 degrees as it flies faster than any human-made object ever built. Its mission is to solve long-standing mysteries about the sun, including why the corona is hotter than the surface, and how solar flares accelerate particles to incredible speeds. In a sense, the probe is not just studying the sun from a distance. It is flying through it, tasting the solar wind, measuring magnetic fields, and sending back data from the edge of a star. The sun also reverberates with the echoes of ancient starlight. The heavier elements found in the sun, oxygen, carbon, nitrogen, and trace metals, did not originate here. They were forged in earlier generations of stars that lived, died, and exploded as supernovae, scattering their enriched material into space, the cloud of gas and dust that eventually collapsed to form the sun carried with it the chemical legacy of those long-dead stars. In this way, the sun is a second or third generation star, built from the remnants of others. We orbit a recycled furnace, a star born from the ashes of older suns. From the sun, we drift inward to Mercury, the smallest of the 8 planets, and the closest to the star that dominates it. Mercury is a world of extremes. During the day, surface temperatures can soar to over 400 degrees, hot enough to melt lead. At night, with no thick atmosphere to trap heat, temperatures plummet to nearly 200 degrees below zero. It is a scorched and frozen world in turns. tidally locked in a strange resonance with the Sun. For every 2 orbits Mercury makes around the Sun, it rotates on its axis exactly 3 times, creating long, strange days that stretch across its surface. Mercury's surface is ancient and cratered, bearing the scars of billions of years of impacts. With no atmosphere to erode the landscape and no tectonic activity to reshape it, craters remain preserved as they were when they formed. The planet's interior, however, is unusual. Mercury has an enormous iron core that makes up about 80% of its radius, far larger in proportion than Earth's core or that of any other rocky planet. Why Mercury has such an oversized core remains uncertain. Some scientists think a giant impact early in its history stripped away much of its rocky mantle. Others believe Mercury formed close to the Sun, where conditions favored the accumulation of heavier, metal-rich materials. Either way, Mercury is a dense, metal-heavy world, a survivor from the solar system's violent youth. Despite the blistering heat, Mercury hides ice. Deep within craters at its poles, where sunlight never reaches, temperatures remain cold enough for water ice to exist. These permanently shadowed regions act as natural freezers, preserving ice for millions of years. Radar observations from spacecraft like Messenger confirmed the presence of these bright, icy patches. Scientists believe the water arrived via comet impacts or was released by ancient volcanic outgassing. In one of the hottest environments in the solar system, ice survives, locked in darkness, shielded from the sun's relentless glare. Mercury also played a quiet but crucial role in confirming one of the most important scientific theories of the 20th century. For centuries, astronomers noticed something odd about Mercury's orbit. Its closest approach to the Sun, called perihelion, shifted slightly over time, more than Newtonian physics could explain. The discrepancy was small but measurable, and it puzzled scientists for decades. In 1915, Albert Einstein's theory of general relativity provided the solution. According to relativity, massive objects like the Sun warp the fabric of spacetime itself, subtly altering the paths of nearby objects. The small shift in Mercury's orbit matched Einstein's predictions exactly. It became one of the first experimental confirmations of general relativity, a triumph of mathematics explaining a quirk in the motion of a scorched, lonely world. Mercury has no true atmosphere, only a ghostly exosphere, a thin shell of particles constantly replenished and lost. Atoms are blasted from the surface by solar wind and micrometeorite impacts, including sodium, potassium, and oxygen. These particles drift around the planet in a near vacuum, bouncing without colliding, before escaping into space. The result is a shimmering, invisible envelope detectable only with sensitive instruments. Mercury stands exposed to the solar wind, unprotected, baking and freezing in turn beneath the gaze of the Sun. Outward now, past Mercury's barren plains, we come to Venus, the second planet from the Sun, and often called Earth's twin, because of its similar size and mass. But the resemblance ends there. Venus is a furnace world, the hottest planet in the solar system despite being farther from the Sun than Mercury. Its thick atmosphere, composed mostly of carbon dioxide, traps heat in a runaway greenhouse effect. Surface temperatures exceed 460 degrees, hot enough to melt lead. The atmospheric pressure at the surface is crushing, more than 90 times that of Earth, equivalent to being a kilometer underwater. clouds of sulfuric acid drift through the upper atmosphere, and the surface is hidden beneath a dense, yellowish haze. Venus rotates in the opposite direction from most planets, a phenomenon called retrograde rotation. On Venus, the sun rises in the west and sets in the east. Even stranger, its rotation is incredibly slow. A single day on Venus, one complete rotation on its axis, takes 243 Earth days. Meanwhile, a Venusian year, one orbit around the sun, takes only 225 Earth days. This means a day on Venus is longer than its year. Scientists are not certain why Venus spins backward. One possibility is a massive collision early in its history that knocked the planet sideways or flipped it entirely. Another theory suggests tidal interactions with the sun gradually altered its spin over billions of years. Whatever the cause, Venus stands alone, a slow-turning world with a reversed rhythm. Venus also lacks something crucial that Earth possesses: a global magnetic field. Despite being similar in size and composition, Venus has no magnetic shield to protect it from the solar wind. Earth's magnetic field is generated by the motion of molten iron in its outer core, but Venus seems to have a sluggish or possibly solid core, preventing the dynamo effect needed to create a field. Without this protection, Venus's atmosphere is constantly bombarded by charged particles from the sun, which have stripped away lighter elements over geological time. The absence of a magnetic field may help explain why Venus, once possibly more Earth-like, became the inferno it is today. Interestingly, Venus has no moons at all. Among the rocky planets, only Mercury and Venus orbit alone. While Mercury's proximity to the Sun might explain its lack of satellites, Venus's situation is more puzzling. It is roughly the same size as Earth, which has a large moon, yet Venus has none. Some theories suggest Venus may have once had a moon that spiraled back into the planet or was lost in a collision. Others propose that Venus is slow. Retrograde rotation prevents stable lunar orbits from forming. Whatever the reason, Venus drifts through space unaccompanied, a bright, cloud-wrapped world with no companion in its twilight sky. From Venus, we move outward to our own world, Earth, the third planet from the Sun, and the only one known to harbor life. Earth is unique in countless ways, but one of its most distinctive features is its system of plate tectonics, a dynamic network of shifting crustal plates that float atop the mantle. These moving plates create earthquakes, build mountains, and recycle carbon dioxide, regulating the climate over geological time. No other planet shows clear evidence of this process. Mars and Venus have surface fractures and volcanic features, but they appear geologically stagnant by comparison. Plate tectonics may be part of what makes Earth habitable, driving the long-term cycles that stabilize temperature, support oceans, and allow continents to drift across the surface over eons. Earth is also the densest planet in the solar system. It packs more mass into each cubic centimeter than any other world, thanks to its composition of a metal-rich core and silicate mantle. This high density plays a key role in generating Earth's magnetic field, which arises from the motion of molten iron in the outer core. The magnetic field acts as a shield, deflecting charged particles from the sun and protecting the atmosphere from being eroded by the solar wind. Without it, Earth might have suffered the same fate as Mars, gradually losing its atmosphere to space. The field also funnels some particles toward the poles, where they collide with atmospheric gases to produce auroras, shimmering curtains of green, red, and violet light that dance across the sky. Earth's axial tilt, about 23.5 degrees relative to its orbit, gives rise to the seasons. When one hemisphere tilts toward the sun, it receives more direct sunlight and experiences summer. When tilted away, the sunlight is weaker and winter arrives. Without this tilt, seasons would be far less pronounced, and much of Earth's climate would be more uniform. The tilt has shifted slightly over time due to gravitational influences from the moon and other planets, but it remains one of the quiet architects of life's seasonal rhythms. Earth is also the only planet where water exists naturally in all three states: solid, liquid, and gas. Ice caps and glaciers, oceans and lakes, clouds and vapor, all coexist and cycle through the atmosphere, land, and sea. This dynamic presence of water is crucial for life and is regulated by Earth's distance from the sun, its atmospheric pressure, and its relatively stable climate. Other worlds may have water in isolated forms, ice crusts, vapor in thin atmospheres, or hidden subsurface oceans, but none show the same planet-wide cycling. On Earth, water flows, freezes, and evaporates in an endless dance that sustains life. Earth's moon is unusually large compared to the size of its host planet. No other rocky world has such a relatively massive satellite. The moon is about 1/4 the diameter of Earth, a ratio more typical of dwarf planet systems than full-sized planets. Most scientists believe the moon formed after a Mars-sized body collided with the young Earth over 4 billion years ago, ejecting debris into orbit that eventually coalesced into the moon. This violent birth had profound consequences. The moon stabilizes Earth's axial tilt, preventing wild climate swings. It drives the tides, mixing ocean waters and influencing coastal ecosystems. The moon is not just a companion. It is a cosmic legacy of collision and renewal, forever bound to Earth by gravity and history. The moon is also slowly drifting away. Each year, it recedes about 3.8 centimeters from Earth, pushed outward by tidal interactions. In the distant past, the moon was much closer and appeared significantly larger in the sky. As it moves away, Earth's days gradually lengthen and eclipses become less frequent. Billions of years from now, the moon will be so distant that total solar eclipses will no longer be possible. The sky is changing, imperceptibly but inevitably, even if we do not yet feel it. The moon's surface changes very little over time. Without wind, rain, or active geology, craters and features remain preserved for millions, even billions of years. Footprints left by astronauts during the Apollo missions will likely remain visible for thousands of generations. Only micrometeorites and cosmic radiation slowly wear down the lunar landscape, a process called space weathering. The moon is not just Earth's closest neighbor, but also one of its oldest and most faithful geological archives, a silent record of the solar system's ancient past. Though the moon appears still, it occasionally trembles with moonquakes. These can be caused by tidal forces from Earth's gravity, thermal expansion as the surface heats and cools, or meteorite impacts. Some quakes originate deep within and can last for over an hour, far longer than earthquakes on Earth. Data from the Apollo missions first revealed these subtle shakes. Though the moon has no tectonic plates, its interior is not entirely dormant. It has a quiet, pulsing heart. The moon also shapes Earth's tides in ways both obvious and subtle. As the moon's gravity tugs on Earth's oceans, It creates bulges on the side facing the moon and on the opposite side. As Earth rotates, these bulges move across the globe, producing the rise and fall of tides. The sun also influences tides, and when the sun and moon align, their combined pull creates especially high spring tides. When they are at right angles, the result is weaker neap tides. Tidal forces affect not only oceans, but also subtly shift Earth's crust and influence the planet's rotation. The moon's silent pull keeps the oceans in constant, rhythmic motion. Beyond Earth, we come to Mars, the fourth planet, the red world that has captured human imagination for centuries. Mars appears red because its surface is coated in fine dust of iron oxide, the same compound that gives rust its color. Over billions of years, this iron-rich material oxidized in the thin Martian atmosphere, creating the planet's signature reddish hue. The dust is so pervasive that it colors the sky during storms and coats the entire landscape. Despite this rusty appearance, Mars also has dark basaltic plains and polar ice caps, creating subtle color variations across its surface. Mars is a world of dramatic geological features. Valles Marineris, stretching more than 4,000 kilometers across the Martian equator, is the largest canyon system in the solar system. It would span the entire width of the continental United States. In places, it plunges over 7 kilometers deep, more than 5 times deeper than the Grand Canyon. Scientists believe it formed through a combination of tectonic stretching, volcanic activity, and erosion. Unlike Earth's canyons, carved by rivers, Valles Marineris may have opened as the planet's crust cracked and pulled apart, a scar hinting at violent geological processes now frozen in time. Mars also hosts Olympus Mons, the tallest volcano in the solar system, towering nearly 22 kilometers above the Martian plains, almost 3 times the height of Mount Everest. It is so wide it would cover the entire state of New Mexico. Olympus Mons grew so large partly because Mars lacks plate tectonics. On Earth, volcanic hotspots shift over time as tectonic plates move, creating chains of islands like Hawaii. But on Mars, the crust remains stationary, allowing magma to erupt in the same spot repeatedly over millions of years. The result is a single massive shield volcano that looms silently over the Martian landscape. Mars experiences seasons much like Earth because it has a similar axial tilt, about 25 degrees compared to Earth's 23. As it orbits the Sun, this tilt causes sunlight to strike different hemispheres more directly at different times of year, creating cycles of spring, summer, autumn, and winter. Martian seasons influence polar ice caps, dust storms, and subtle changes in atmospheric pressure. However, they unfold more slowly than on Earth, because Mars takes nearly twice as long to complete a year. Mars is also known for colossal dust storms that sometimes engulf the entire planet. These storms can last for weeks or even months, blocking out sunlight and reshaping the surface. The dust is incredibly fine and stays suspended in the atmosphere, creating a hazy reddish glow. Some storms begin as small gusts but grow rapidly due to feedback loops between heat, wind, and topography. In 2018, such a storm ended the mission of the Opportunity rover as its solar panels were choked with dust. Even without rain or oceans, Mars remains an active and restless world. Mars has 2 small, misshapen moons, Phobos and Deimos. They look more like captured asteroids than traditional moons, irregular, rocky, and pockmarked with craters. Many scientists believe they were once part of the asteroid belt and were snared by Mars's gravity long ago. Phobos is slowly spiraling inward and will eventually break apart or crash into Mars. Deimos is drifting away. These little moons are quiet passengers, remnants of a chaotic past, drifting in orbit around the red planet. Between Mars and Jupiter lies the asteroid belt, a vast region populated by millions of rocky bodies. Despite popular imagination, the asteroid belt is mostly empty space. A spacecraft passing through would almost never encounter an obstacle. The entire mass of the belt is less than 5% that of Earth's moon. Its largest members, like Ceres and Vesta, account for most of that mass. The rest are scattered fragments from the early solar system, ancient building blocks that never coalesced into a planet. Ceres is unique. It is both an asteroid and a dwarf planet, the largest object in the belt. Discovered in 1801, Ceres is spherical, unlike smaller asteroids, and may contain a subsurface layer of briny water or mud. The Dawn spacecraft revealed mysterious bright spots on its surface, which turned out to be salt deposits, possibly left behind by evaporating water. Ceres is a hybrid world, offering glimpses into the early ingredients of planetary formation. Vesta, the second largest object in the belt, has a layered internal structure similar to a planet. Beneath its surface lies a mantle and dense metallic core, meaning Vesta once had enough internal heat to melt and differentiate into layers. A giant impact carved out the Re Silvia crater at its south pole, possibly exposing some of these deeper layers. Vesta is a frozen protoplanet, a planetary building block that never quite finished forming. Some asteroids even have their own moons. While we often picture asteroids as solitary wanderers, some have smaller bodies orbiting them. The first discovered was Dactyl, orbiting the asteroid Ida, revealed by the Galileo spacecraft in 1993. Since then, dozens more have been found, including binary systems where two asteroids orbit each other. These miniature systems show that even in the vastness of space, gravity can link the smallest objects into quiet, drifting partnerships. Not all asteroids are solid rock. Many are loose collections of stones, gravel, and dust held together only by gravity, structures known as rubble piles. These fragile bodies form after collisions shatter larger asteroids, with debris slowly coming back together over time. Rubble pile asteroids can have large internal voids and spin strangely. Missions like Hayabusa 2 and OSIRIS-REx have visited such bodies, confirming their delicate nature. These asteroids are chaotic assemblages, ancient drifting ruins that barely hold themselves together as they orbit the sun. Beyond the asteroid belt, we enter the realm of the gas giants, and first among them is Jupiter, the largest planet in the solar system. Jupiter is so massive that all the other planets combined would fit inside it with room to spare. It contains more than twice the mass of all other planets, moons, asteroids, and comets put together. Yet despite this immensity, Jupiter is not a solid world. It is composed mostly of hydrogen and helium, the same primordial gases that make up the Sun. Deep within, under crushing pressure, hydrogen transitions into a metallic liquid state, generating powerful electric currents that create Jupiter's immense magnetic field. Jupiter's magnetosphere is the largest structure in the solar system. It extends millions of kilometers into space, forming a bubble so vast that if it were visible, it would appear larger than the sun in Earth's night sky. Within this magnetosphere, charged particles race along magnetic field lines, creating intense radiation belts, far more powerful than Earth's Van Allen belts. These radiation zones are so harsh they would destroy unprotected spacecraft in hours. Jupiter's largest moons orbit within this radiation, their surfaces constantly bombarded by energetic particles. To survive near Jupiter, spacecraft must be specially shielded or follow carefully planned trajectories through lower radiation paths. Jupiter is also unusual in that it radiates more energy than it receives from the sun. This internal glow comes from leftover heat from the planet's formation, gravitational energy released as Jupiter's immense mass slowly contracts. This warmth drives Jupiter's turbulent weather systems, including its giant storms and swirling cloud bands in the infrared spectrum. Jupiter shines like a smoldering ember beneath its cloud layers. It is not a star, but it nearly became one. If Jupiter had been just slightly more massive, it might have ignited nuclear fusion and become a failed star, a brown dwarf glowing dimly in the darkness. Jupiter's atmosphere is a canvas of constantly shifting storms and jet streams. Cloud bands circle the planet in alternating zones of rising and falling gas, driven by internal heat and rapid rotation. Jupiter spins faster than any other planet, completing a full rotation in less than 10 hours. This rapid spin stretches the planet at its equator and flattens it at the poles, giving it a noticeably oblate shape. The most famous feature in Jupiter's atmosphere is the Great Red Spot, a massive storm swirling in the planet's southern hemisphere. It is wide enough to swallow 2 or even 3 Earths, and has been raging for at least 350 years, possibly much longer. First observed in the 1600s through early telescopes, the storm has changed over time, gradually shrinking, but remaining powerful. Wind speeds along its outer edges exceed 400 kilometers per hour. Its reddish hue may be caused by complex chemical reactions triggered by sunlight interacting with compounds high in the atmosphere. While Earth's storms last days or weeks, this Jovian tempest has spanned centuries, trapped in the planet's turbulent belts. Jupiter is also the king of moons. As of now, astronomers have identified more than 90 natural satellites orbiting the giant planet, and new ones are still being discovered. The 4 largest, Io, Europa, Ganymede, and Callisto, are known as the Galilean moons, named after Galileo Galilei, who first observed them in 1610. Beyond these giants lies a swarm of smaller, irregular moons, many of them captured objects from passing asteroids or comets. Some orbit backward in retrograde motion. Some are just a few kilometers across. Together, they form a miniature solar system bound by Jupiter's immense gravity. Io, the innermost of the Galilean moons, is the most volcanically active world in the solar system. Its surface is constantly reshaped by eruptions of molten sulfur and rock, painting the landscape in vivid yellows, reds, and blacks. Some volcanic plumes rise hundreds of kilometers into space. This extreme activity is driven by tidal heating. Io is squeezed and stretched by Jupiter's gravity, and gravitational tugs from neighboring moons create friction that heats the interior, powering furious geology. Unlike Earth's cooling crust, Io's surface is young, volatile, and ever-changing, a lava-lit moon with a molten heart. Europa, the next moon outward, may hide one of the solar system's most tantalizing secrets. Beneath its frozen shell lies strong evidence for a vast subsurface ocean of liquid water. Tidal forces from Jupiter's gravity flex Europa's interior, generating heat that keeps the ocean from freezing solid. The surface is crisscrossed with dark lines and ridges, signs of shifting ice. Spacecraft have detected magnetic signatures and chemical traces that support the ocean hypothesis. What makes Europa especially fascinating is the possibility that this hidden sea could harbor life. It is a dark, alien ocean warmed from below, sealed beneath ice, yet potentially rich with the ingredients for biology. Europa's cracked surface may even exhibit a form of ice tectonics, with plates of ice breaking, sliding, and possibly subducting like Earth's crustal plates. If true, Europa would be the only known body besides Earth with active plate-like motion. This process could cycle nutrients between the surface and the ocean below, increasing the moon's potential for habitability. The driving force is tidal flexing from Jupiter, which continually needs Europa's interior, keeping it geologically active despite the deep cold of the outer solar system. Ganymede, the largest moon, not just of Jupiter but of the entire solar system, is even bigger than the planet Mercury. With a diameter of over 5,000 kilometers, Ganymede has a rocky core, a possible subsurface ocean, and a crust covered in ridged ice and ancient scars. Uniquely among moons, Ganymede has its own magnetic field, which creates shimmering auroras in its thin atmosphere. Scientists believe Ganymede may have multiple layers of ocean sandwiched between sheets of ice, forming a complex internal world. Despite its size and richness, Ganymede remains quiet and dark, orbiting deep within Jupiter's magnetic grasp. Callisto, the outermost of the Galilean moons, appears quiet and heavily cratered, its ancient surface seemingly untouched by recent geological activity. But deep beneath that frozen crust, scientists suspect a subsurface ocean may exist, kept liquid by internal heating and residual warmth from formation. Magnetic readings from the Galileo spacecraft hinted at a conductive layer beneath the surface, consistent with salty water. If confirmed, Callisto would join Europa and Ganymede as another ocean world. Though less well known, Callisto's deep, dark sea could contain ingredients for life, silently sealed beneath a shell of ice and time. Moving outward from Jupiter, we come to Saturn, the second largest planet, and perhaps the most visually striking object in the solar system. Saturn is famous for its magnificent rings, broad bands of ice and rock that encircle the planet in a thin, flat disk. These rings stretch more than 280,000 kilometers across, yet in most places they are less than 100 meters thick, thinner than many city buildings. Made mostly of water ice, the ring particles range in size from grains of dust to house-sized boulders. When sunlight passes through the ring plane edge-on, they nearly vanish from view, like a sheet of glass turned sideways. The rings are not permanent. They are gradually falling into Saturn, drawn inward by gravity and magnetic forces known as ring rain. Observations from the Cassini spacecraft suggest the rings may be less than 100 million years old, young by planetary standards, and could vanish entirely within another few 100 million years. Though they seem timeless, Saturn's rings are a temporary feature, a shimmering spectacle that will one day fade from the solar system. Saturn's rings are also dynamic and complex. Embedded within them are narrow gaps, wave patterns, and ringlets shaped by gravitational resonances with Saturn's many moons. Small shepherd moons orbit within and near the rings, their gravity carving gaps and maintaining sharp edges. The rings are not solid structures, but countless individual particles orbiting in formation, sculpted by gravity into one of the most beautiful sights in nature. Saturn itself is less dense than water. If you could place it in a giant cosmic bathtub, it would float. This is not because it is hollow, but because it is composed mostly of hydrogen and helium, giving it remarkable lightness despite its massive size. Saturn's volume is enormous, more than 700 times that of Earth, but its mass is only about 95 times greater. This low density gives Saturn a gentle, diffuse structure. Rapid rotation flattens it at the poles and bulges it at the equator, creating a noticeably oblate shape. Saturn's atmosphere holds one of the more surreal phenomena in the solar system. At its north pole, a massive cloud pattern spins in the shape of a nearly perfect hexagon. This six-sided jet stream spans over 30,000 kilometers across, wider than Earth itself, and has persisted for decades, possibly centuries. Scientists believe the hexagon forms from the way Saturn's atmosphere rotates and interacts with stable waves of air trapped around the pole. Laboratory experiments with rotating fluids at different speeds have produced similar geometric shapes. The fact that such a regular form can emerge naturally in a planetary atmosphere remains one of the more elegant mysteries of planetary science. Saturn has more than 80 known moons, ranging from tiny captured asteroids to massive worlds. The largest, Titan, is the second largest moon in the solar system, and the only one with a thick atmosphere. Titan's atmosphere is rich in nitrogen and forms weather systems that include methane rain and seasonal storms. But what makes Titan truly extraordinary is that it is the only other place in the solar system known to have stable liquids on its surface. These are not oceans of water, but lakes and rivers of liquid methane and ethane, flowing across a landscape sculpted by cold chemistry. Some of Titan's lakes are vast, stretching hundreds of kilometers. The moon has familiar shapes, clouds, rivers, coastlines, but all built from alien substances. Beneath the icy surface, scientists believe a subsurface ocean of water may also exist, making Titan a world with two kinds of oceans stacked one above the other. Another of Saturn's moons, Enceladus, is small but hides a spectacular secret. From its south pole, towering geysers of water vapor and ice crystals erupt into space through cracks, known as tiger stripes. These plumes are powered by tidal heating beneath the surface, where friction caused by Saturn's gravitational pull keeps a subsurface ocean in a liquid state. The material in the plumes contains organic compounds, salts, and even signs of hydrothermal activity, raising the possibility of life. Some of the water escapes into space and helps replenish Saturn's E-ring, creating a living connection between moon and planet. Enceladus is a tiny world with an active heart, spraying evidence of its hidden ocean into the void. Beyond Saturn, the solar system grows darker and colder. We reach Uranus, the seventh planet from the Sun and one of the strangest worlds in the solar system. Most planets spin like tops, tilted slightly on their axes. But Uranus is tipped so far over that it essentially rolls along its orbital path with an axial tilt of 98 degrees. This means its poles point almost directly at the Sun during parts of its orbit, giving it extreme and bizarre seasons. Each pole experiences 42 years of continuous daylight, followed by 42 years of darkness. The cause of this tilt is still debated, but it may have been knocked sideways by a massive collision long ago. Uranus's tilted orientation gives it one of the strangest climates in the solar system. Uranus is classified as an ice giant, along with Neptune. Unlike Jupiter and Saturn, which are mostly hydrogen and helium, Uranus has a thick mantle of water, ammonia, and methane ices surrounding a small rocky core. The methane in its upper atmosphere absorbs red light, giving Uranus a pale blue-green color. The planet appears relatively featureless compared to Jupiter or Saturn, with only faint cloud bands and occasional storms visible in its hazy atmosphere. Deep within Uranus and Neptune, conditions may be extreme enough to create something extraordinary. Falling diamonds. These ice giants have thick layers of methane gas, and under immense pressure and heat, scientists believe the methane can break apart, releasing carbon atoms. These carbon atoms then compress into crystalline structures, forming tiny diamonds that rain down toward the core. Laboratory experiments have simulated this process, showing how hydrocarbons can condense into diamond under the right conditions. If this theory is correct, storms of glittering crystals might drift through the deep blue darkness of distant gas giants. Uranus also has a ring system, though it is much fainter than Saturn's. 13 known rings orbit the planet, made of tiny particles of rock and ice. These rings orbit in alignment with Uranus's unusual tilt, so they appear vertical when viewed from certain angles. Some rings are narrow and sharp-edged, possibly shaped by small shepherd moons. The rings were not discovered until 1977, when they blocked the light of a background star during an occultation. They are subtle, shadowy bands circling a sideways planet. Uranus was the first planet discovered in modern times. Unlike the planets visible to the naked eye since antiquity, Uranus was not identified until 1781, when astronomer William Herschel observed it through a telescope. At first, he thought it might be a comet or star, but further observations confirmed its planetary motion. Uranus became the first planet discovered with a telescope, expanding the known boundaries of the solar system and marking a shift from naked-eye astronomy to instrument-based exploration. Since then, Uranus has revealed many surprises, from its extreme tilt to its faint rings and icy moons. Uranus has 27 known moons, all named after characters from the works of William Shakespeare and Alexander Pope. Most are small and icy, orbiting in the planet's tilted equatorial plane. Some show signs of past geological activity, with ridges, valleys, and resurfaced terrain hinting at internal processes that have since frozen. These moons drift in the dim light far from the sun, cold and distant worlds in a strange system ruled by a planet that rolls on its side. Beyond Uranus lies Neptune, the eighth and outermost planet in the solar system. Neptune was discovered not by direct observation, but through mathematics. In the 1840s, astronomers noticed irregularities in Uranus's orbit, tiny deviations that could not be explained by the gravity of known planets. Two mathematicians, working independently, used these perturbations to predict the location of a hidden planet. When when astronomers pointed their telescopes toward the calculated position. Neptune was there. It was a triumph of celestial mechanics. The first planet found on paper before it was seen through glass. A world brought to light by numbers and equations. Neptune is similar in size and composition to Uranus, another ice giant with a thick mantle of water, ammonia, and methane surrounding a rocky core. But Neptune is far more active. Despite being the farthest major planet from the Sun, Neptune hosts the fastest winds in the solar system, whipping through its upper atmosphere at speeds exceeding 2,000 kilometers per hour, faster than the speed of sound on Earth. These winds carve massive storm systems into the planet's pale blue clouds, driven by internal heat that continues to radiate outward despite the freezing conditions at its surface. In fact, Neptune radiates about 2.6 times more energy than it receives from the Sun. This internal heat drives strong winds and powerful storms, making Neptune a world of surprising energy despite its extreme distance. The exact source of this heat remains uncertain, but possibilities include residual energy from formation, slow gravitational contraction, or radioactive decay within the core. Neptune is a planet with a cold exterior and a warm, restless interior, constantly reshaping its windswept atmosphere. Neptune's atmosphere is composed mostly of hydrogen, helium, and methane. The methane absorbs red light, giving Neptune a deeper, richer blue color than Uranus. Cloud systems drift through the atmosphere, including large storms that appear and disappear over time. The Voyager 2 spacecraft observed a massive storm called the Great Dark Spot during its flyby in 1989. But when the Hubble Space Telescope looked at Neptune years later, the storm had vanished, replaced by others elsewhere on the planet. Neptune's weather is dynamic and ever-changing, driven by forces we still do not fully understand. Neptune has 14 known moons. The largest, Triton, is one of the strangest objects in the solar system. Triton is unique among large moons because it orbits Neptune in the opposite direction of the planet's rotation, a retrograde orbit. This backward motion suggests Triton did not form alongside Neptune, but was captured from the Kuiper Belt long ago. The capture may have caused dramatic upheaval, disrupting Neptune's original satellite system and tilting Triton's interior, causing tidal heating. Today, Triton is geologically active, with cryovolcanoes that spew nitrogen gas and icy material into space. It has a thin atmosphere that drifts in and out with the seasons, and a frozen surface marked by strange cantaloupe-like textures. Cold, distant, and moving in reverse, Triton is a world that defies expectations at every turn. Beyond Neptune lies the Kuiper Belt, a vast ring of icy objects that stretches billions of kilometers from the Sun. It is home to countless frozen bodies, including dwarf planets like Pluto, Eris, Haumea, and Makemake. These are not stars or planets, but ancient remnants from the solar system's formation. Some are spherical and classified as dwarf planets. Others are irregular, tumbling through space in slow rotation. The Kuiper Belt is similar in structure to the asteroid belt, but far colder, and contains more primordial ice. It is a fossil zone, a frozen archive of the materials that built the outer worlds. Pluto, the most famous resident of the Kuiper Belt, was long considered the ninth planet, until it was reclassified as a dwarf planet in 2006. Pluto is small, smaller than Earth's moon, but it is a complex and geologically active world. The New Horizons spacecraft flew past Pluto in 2015, revealing a surface of nitrogen ice plains, towering water ice mountains, and a bright heart-shaped feature called Sputnik Planitia. This region may be the surface expression of a vast subsurface ocean. Though Pluto is far from the sun and cold enough to freeze nitrogen, evidence suggests a layer of liquid water might lie beneath its icy crust. If this ocean exists, it could be kept liquid by heat from radioactive decay and insulating ice layers above. Even in the frozen reaches beyond Neptune, hidden seas may quietly persist. Pluto has a thin atmosphere composed mostly of nitrogen with traces of methane and carbon monoxide. When Pluto approaches the Sun in its elliptical orbit, surface ices sublimate into gas, forming a hazy envelope that expands into space. But as Pluto moves farther out, the atmosphere cools and collapses, freezing back onto the surface like frost. This cycle repeats over Pluto's 248-year orbit. During the New Horizons flyby, Pluto's atmosphere was visible as a layered blue haze, a fleeting breath of warmth around a world that spends most of its time in deep cosmic winter. Pluto's orbit is highly elliptical, meaning it sometimes travels closer to the Sun than Neptune. This last occurred between 1979 and 1999, when Pluto was temporarily the 8th planet from the Sun instead of the 9th. Even so, the two worlds never collide or come dangerously close because their orbits are in resonance. For every 3 orbits Neptune makes, Pluto completes exactly 2. This gravitational choreography keeps them in a stable dance, their paths never crossing. It is a delicate balance governed by celestial rhythm and time. Pluto has 5 known moons, the largest of which is Charon, about half Pluto's size. Charon is so large relative to Pluto that they are sometimes considered a binary system, 2 worlds orbiting a common center of mass between them. Charon may have formed from debris after a giant impact, similar to how Earth's moon formed. The two are tidally locked, always showing the same face to each other as they orbit. Pluto and Charon drift through the Kuiper Belt together, a binary pair in the outer darkness. Beyond the Kuiper Belt lies an even more distant and mysterious region. Far beyond Pluto's furthest reach lies a hypothetical shell of icy bodies known as the Oort cloud. Though never directly observed, this vast sphere of frozen debris is thought to encircle the entire solar system, extending nearly a light year away. It is the likely source of long-period comets, which appear from the depths of space with unpredictable orbits. These distant objects are only weakly bound to the Sun, and a passing star or galactic tide could send one hurtling inward toward the inner solar system. If the Oort cloud exists, it marks the true edge of the Sun's gravitational influence, a distant halo of icy wanderers drifting in the space between stars. Long-period comets, the kind that appear only once every few thousand years, are believed to come from the Oort cloud. These comets travel on elongated, loosely bound orbits, and are often dislodged from their resting places by gravitational nudges from passing stars or tidal forces from the galaxy itself. When they fall inward toward the Sun, they can light up with spectacular tails visible even from Earth. Some may have spent billions of years drifting in darkness before being disturbed into motion. Their bright returns are fleeting glimpses of the solar system's most ancient, untouched matter, messengers from the edge of the Sun's domain. As a comet approaches the Sun, its icy surface begins to sublimate, releasing gas and dust that form a glowing tail. But contrary to intuition, the tail does not trail behind the comet like smoke behind a train. It points away from the sun, no matter which direction the comet is moving. This is because solar wind and radiation pressure push the material outward, forming two distinct tails. One is a curved dust tail, made of heavier particles that follow slightly different paths. The other is a straight, bluish ion tail, made of electrically charged gas pushed directly away by the solar wind. The result is a luminous, windswept signature tracing the invisible force of sunlight through the darkness of space. The boundary where the solar wind meets the interstellar medium is called the heliopause, and it marks the outer edge of the sun's protective bubble, the heliosphere. As the solar wind flows outward from the sun, it eventually collides with the thin gas and dust between stars. Beyond this boundary, the pressure from other stars and galactic particles becomes stronger than the solar wind. Voyager 1 crossed the heliopause in 2012, followed by Voyager 2 in 2018, entering true interstellar space. Though the sun's gravity still extends much farther, holding the Oort cloud in its distant embrace, the heliopause marks the end of the sun's energetic reach, the final breath of solar influence before deep space begins. The heliosphere itself is a vast magnetic bubble blown by the sun. The solar wind, a stream of charged particles continuously released by the sun, flows outward in all directions, forming this protective shield around the entire solar system. Shaped by solar activity and the pressure of interstellar space, it stretches far beyond Pluto, enclosing all the planets, comets, and distant objects. As the sun orbits the Milky Way galaxy, the heliosphere moves with it, protecting the solar system as it drifts through changing regions of interstellar space. Our entire solar system is moving through a region called the local interstellar cloud, a thin concentration of gas and dust about 30 light-years across. It is part of a larger structure known as the local bubble, a cavity in the interstellar medium formed by ancient supernova explosions that swept away surrounding material. As the sun travels through this cloud at about 7,000 kilometers per hour, the heliosphere acts like a bow wave on a ship, deflecting interstellar material around the solar system. Scientists study this cloud to understand how interstellar conditions affect cosmic rays, the shape of the heliosphere, and even subtle influences on Earth's climate over geological time. We are not sitting still in space. We are sailing slowly and silently through a galactic fog. The sun itself is also in motion on a grander scale. While the planets orbit the sun orbits the center of the Milky Way galaxy, completing one full revolution roughly every 225 to 250 million years, a journey sometimes called a cosmic year or a galactic year. During that time, the solar system drifts through different regions of interstellar space, potentially passing through spiral arms, star-forming regions, and clouds of gas and dust. This motion may influence long-term patterns in comet activity and, on even longer timescales, may affect Earth's climate. We are not fixed in space, but are part of a vast, slow spiral, riding the galaxy's arm like passengers on a cosmic carousel. Leaving the solar system is no small task. Spacecraft like Voyager 1 and 2, launched in the 1970s, have only recently entered interstellar space, more than 40 years after they left Earth. traveling at speeds exceeding 60,000 kilometers per hour. They crossed the orbits of all the planets, passed through the Kuiper Belt, and continued into the dark. They carry instruments still functioning after all these decades, as well as a golden record filled with sounds of Earth, greetings in dozens of languages, music from around the world, and recordings of waves, birdsong, and laughter. Designed by a team led by Carl Sagan, the record is meant for any intelligent beings who might someday find it. It is a message in a bottle cast into the galaxy, a quiet greeting from our pale blue dot. Voyager 1 is now the most distant human-made object, traveling through the interstellar medium billions of kilometers from home. Its instruments measure cosmic rays, magnetic fields, and the plasma density in the space between stars. Power is limited, supplied by a tiny nuclear generator, and systems are gradually being turned off to conserve energy. Every signal it sends takes more than 22 hours to reach Earth, a whisper from the edge of human exploration, but it continues to transmit, still sending data from a realm no spacecraft has ever visited before. Astronomers have noticed that some distant objects in the Kuiper Belt follow clustered, elongated orbits that cannot be easily explained by the known planets. One leading theory is that a large, as yet undetected planet, sometimes called Planet 9, may be influencing these distant paths with its gravity. If it exists, this hidden planet would be several times the mass of Earth and would orbit far beyond Pluto, taking thousands of years to complete a single revolution. No direct evidence has yet confirmed it, but telescopes continue to search the sky. If found, it would reshape our understanding of the solar system's outer architecture and add a ninth major world to the family of planets. There are more dwarf planets than classical planets. Beyond Neptune lies a scattered population of icy, distant objects, many large enough to qualify as dwarf planets. Pluto is the most famous, but it is just one among many. Others like Eris, Haumea, and Makemake share this status, and more candidates are constantly being discovered in the Kuiper Belt and beyond. In fact, the number of dwarf planets may vastly exceed that of the 8 classical planets. These small, round worlds are relics of the early solar system, untouched and ancient. Though they orbit in the cold shadows, they hold clues to the formation of everything we know. Some of these distant worlds have startlingly bright surfaces. Eris, for example, reflects nearly all the sunlight that hits it, making it one of the most reflective bodies in the solar system, brighter than freshly fallen snow. Haumea is an oddly shaped, fast-spinning object elongated like a football and coated in crystalline water ice. These objects may have been resurfaced by cryovolcanism, impacts, or chemical interactions. In the darkness at the edge of the sun's reach, some distant worlds gleam like cold mirrors, catching faint sunlight in their frozen silence. The solar system is about 4.6 billion years old. By studying ancient meteorites, radioactive isotopes, and the oldest rocks on Earth and the Moon, scientists have traced its age to this remarkable precision. It began as a swirling cloud of gas and dust, a solar nebula, which collapsed under its own gravity. The sun formed at the center, and the remaining material coalesced into planets, moons, asteroids, and comets through a process of accretion and differentiation. This process laid the foundation for everything that followed. The planets we see today are survivors of a chaotic beginning, shaped by countless collisions, migrations, and slow cooling over billions of years. Planetary orbits are not perfect circles. Although we often imagine planets moving in neat circular paths around the sun, Their orbits are actually ellipses, slightly stretched circles with the sun offset from the center. This elliptical shape means each planet has a point where it is closest to the sun, called perihelion, and a point where it is farthest, called aphelion. For most planets, the difference is subtle, but for others like Mercury and Pluto, it is more dramatic. These variations influence seasons, solar radiation, and orbital speed. The elliptical nature of planetary motion was first described by Johannes Kepler in the early 1600s, reshaping humanity's understanding of the solar system's elegant mechanics. Some moons formed from giant impacts. Earth's moon is believed to have formed from a colossal collision between the early Earth and a Mars-sized body over 4 billion years ago. The impact ejected material into orbit, which gradually coalesced into the moon. Similar impact origins are suspected for other moons, such as Pluto's largest moon, Charon. These violent beginnings contrast with the captured moons of the outer planets, showing that no single process explains all satellites. Some moons were born of fire and collision, others from gentle gravitational capture. The diversity of their origins mirrors the chaos and creativity of the solar system's formative years. Some moons may have formed from ring systems. Just as ring systems can decay and vanish over time, they can also give birth to moons. It is possible that some of Saturn's smaller outer moons originally coalesced from ring material that clumped together beyond the Roche limit, the boundary beyond which gravity can pull matter into moons rather than tearing it apart. Moons like Pan and Daphnis, which orbit within Saturn's rings, may still be accreting material from them today. These moonlets serve as quiet sculptors of the rings, their gravity carving gaps and waves into the icy bands around them. Planetary rings themselves may be temporary features. Though they appear timeless, the rings around Saturn, Jupiter, Uranus, and Neptune may be relatively short-lived on cosmic timescales. Rings formed from shattered moons, leftover debris, or icy particles pulled into orbit. But over millions of years, these materials can spiral inward due to gravity, magnetic drag, or collisions, eventually falling onto the host planet. Observations suggest Saturn's rings may be less than 100 million years old and could vanish within another 100 million. The rings we see today may be a fleeting phase, a spectacular, shimmering moment in a planet's much longer life. Most of the solar system's moons orbit the gas giants. While Earth has just one moon and Mars has two tiny ones, the giant planets of the outer solar system are surrounded by sprawling systems of satellites. Jupiter and Saturn each have dozens of confirmed moons, ranging from tiny captured asteroids to massive worlds like Ganymede and Titan. Uranus and Neptune also host many icy moons, some with complex orbits and hidden oceans. These gas giants act like miniature solar systems, their gravity drawing in debris and coalescing satellites over time. The farther from the sun you travel, the more moons you find, a reminder that gravity gathers companions in the cold. Some moons are geologically active despite their small size and great distance from the sun. Activity is not limited to planets. Several moons show signs of internal energy and surface change. Io is riddled with active volcanoes fueled by tidal heating. Enceladus vents plumes of water vapor into space from its subsurface ocean. Europa and Ganymede likely have subsurface seas stirred by internal warmth. Even distant Triton shows signs of cryovolcanism. icy eruptions driven by shifting pressures below. These moons are not static ice balls. They are restless worlds with geology, chemistry, and perhaps even the potential for biology hidden beneath their frozen exteriors. Beneath the icy crusts of moons like Europa and Enceladus, scientists believe subsurface oceans may touch hot rocky cores, forming hydrothermal vents similar to those found on Earth's ocean floors. On our planet, such vents support entire ecosystems without sunlight, using chemical energy from minerals and heated water. If similar vents exist on these distant moons, they could provide the conditions necessary for life. Water, heat, and a steady energy source, plumes from Enceladus, even contain organic compounds and other molecules associated with biological processes. These hidden underwater worlds may be the most promising places to search for life beyond Earth. Some meteorites on Earth actually came from Mars. Though Mars is millions of kilometers away, pieces of it have landed on our planet. These are Martian meteorites, fragments of rock blasted off the surface by powerful impacts, which then traveled through space and eventually fell into Earth's atmosphere. Scientists identify them by comparing their chemical composition to data collected by Mars rovers and orbiters. Some of these meteorites contain tiny bubbles of trapped Martian air and minerals shaped by water, offering direct clues to Mars's geological and chemical history. These wayward stones are samples from another world, sent to us by nature long before any spacecraft returned the favor. The sun is mostly hydrogen and helium. About 70% of the sun's mass is hydrogen, and most of the rest is helium. These two lightest elements dominate its makeup and fuel the nuclear fusion at its core. Under extreme pressure and heat, hydrogen atoms fuse into helium, releasing vast amounts of energy. The remaining 1 to 2% of the sun's mass includes oxygen, carbon, nitrogen, and heavier elements, all of which originated in earlier generations of stars. Despite its brilliance and complexity, the sun is fundamentally simple in composition, a glowing sphere of primordial gases shaped by gravity and nuclear fire. Temperatures at the sun's core exceed 15 million degrees. Deep inside, at its center, hydrogen atoms are compressed under immense pressure until they fuse into helium, releasing enormous amounts of energy in the process. This fusion is what powers the sun's light and heat, and ultimately all life on Earth. The energy generated in the core takes hundreds of thousands of years to reach the surface, bouncing through layers of dense plasma before finally escaping. Once it does, it travels across space in just over 8 minutes to reach us. The sun's radiant calm hides an unimaginably hot and violent heart. Sunlight takes over 8 minutes to reach Earth. The light that warms your skin and brightens the sky began its journey in the sun's core, where nuclear fusion creates photons. These photons then spend hundreds of thousands of years traveling from the sun's center to its surface, bouncing and scattering through dense plasma. Once they escape the surface, however, they travel the remaining distance to Earth, about 150 million kilometers, in just over 8 minutes. When you watch a sunrise or look at the midday sun, you are seeing it not as it is now, but as it was 8 minutes ago, a glimpse into the very recent past. Solar flares are sudden, powerful eruptions of energy from the sun's surface, often linked to sunspot activity. These outbursts release intense bursts of radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. When directed toward Earth, they can disturb the upper atmosphere, affecting GPS systems, radio communications, and satellite operations. In extreme cases, they can trigger geomagnetic storms, potentially damaging power grids and other infrastructure. While Earth's magnetic field offers substantial protection, solar flares remind us that the sun is not a steady, passive light bulb, but a dynamic, volatile star, one that occasionally sends ripples of energy pulsing across the solar system. The solar cycle influences auroras on Earth. Auroras, the shimmering curtains of green, red, and violet light near Earth's poles, are caused by charged solar particles interacting with Earth's magnetic field and atmosphere. These displays become more frequent and intense during periods of high solar activity, which follow an 11-year cycle. During solar maximum, increased sunspot activity and solar flares send more particles hurtling toward Earth, fueling brighter auroras. During solar minimum, the lights are quieter and less frequent. The sun's magnetic fluctuations ripple outward across the solar system, and we see them painted in the skies, a reminder that space weather can illuminate the heavens in subtle, solar brushstrokes. Earth's magnetic field shields us from much of this radiation. Surrounding our planet is an invisible magnetic field generated by the movement of molten iron in Earth's outer core. This field deflects charged particles from the sun, protecting the atmosphere and surface from harmful solar and cosmic radiation. Without it, the solar wind would gradually erode our atmosphere, as it likely did on Mars billions of years ago. The magnetic field also funnels some particles toward the poles, where they interact with atmospheric gases to produce auroras. Earth's magnetosphere is a dynamic, invisible shield, essential for preserving both life and climate over geological time. Even thick atmospheres like Earth's are not permanent. Over time, light gases like hydrogen and helium can escape a planet's gravity and drift off into space, a process known as atmospheric escape. This is more pronounced on smaller planets with weaker gravity, such as Mars and Mercury. On Venus, a lack of magnetic shielding has allowed the solar wind to erode parts of its upper atmosphere over billions of years. Earth loses thousands of tons of hydrogen each year, though it is easily replenished through geological and biological processes. The slow escape of gases is a quiet leak into the void, a constant exchange between planets and the vacuum beyond. Planetary alignments do not cause natural disasters. It is a common myth that when planets align in their orbits, their combined gravitational pull can trigger earthquakes, floods, or other catastrophes on Earth. But there is no scientific evidence for such effects. The gravitational pull of other planets on Earth is minuscule compared to the Moon or the Sun. Even during rare alignments, their combined influence is negligible. The Moon, being so close, has far more impact on tides and subtle seismic stress than massive but distant planets like Jupiter or Saturn. Planetary alignments are beautiful and mathematically interesting, but they are gravitationally harmless, a silent dance of distant worlds, not a celestial omen, though it orbits just above Earth's atmosphere. The Hubble Space Telescope has captured detailed images of the outer planets, including cloud bands on Jupiter, storms on Neptune, and seasonal changes on Mars. These images provide long-term observations that complement spacecraft flybys, offering views of evolving weather patterns, ring systems, and planetary auroras. Hubble's clarity allows scientists to track storm development, monitor impact events, and study atmospheres in ultraviolet and visible light. From its quiet perch in low Earth orbit, Hubble watches not only the distant galaxies, but also the shifting faces of our neighboring worlds, documenting changes across decades. Earth shares its orbital space with small bodies known as co-orbital asteroids. These objects do not orbit Earth like moons, but instead follow stable, looping paths near Earth's orbit, shaped by gravitational interactions with both Earth and the Sun. Some, called Trojans, hover around stable Lagrange points ahead of or behind Earth in its orbit. Others follow horseshoe-shaped paths that keep them near but never colliding with our planet. These quiet companions are often temporary, captured and released over thousands of years. Invisible to the naked eye, they drift near us in space, fellow travelers on our yearly journey around the Sun. Before Neptune was officially discovered in 1846, some early astronomers may have observed it without realizing what it was. Because it moves so slowly across the sky and appears so dim, it was occasionally mistaken for a fixed star or thought to be another sighting of Uranus. In fact, Galileo may have unknowingly seen Neptune through his telescope in 1612 and marked it in his notes as a star. It was not until mathematicians noticed irregularities in Uranus's orbit that Neptune's existence was predicted and confirmed. In the sky filled with wandering points of light, Neptune remained hidden in plain sight for centuries, waiting to be recognized. The edge of the solar system is not defined by gravity alone. The Sun's gravitational pull extends far beyond Pluto, holding on to distant comets and icy bodies in the Oort cloud. But when scientists speak of the edge of the solar system, they often refer to the boundary of the heliosphere, the region where the solar wind meets the interstellar medium. This edge, the heliopause, marks the point where the Sun's magnetic field and particle flow end, and the influence of other stars begins. Gravity continues far beyond, but the energetic boundary is where the space between stars truly begins. It is a subtle, shifting frontier, more a change in pressure than in presence. The solar system itself is not isolated. It exists within a larger galactic context, moving through the Milky Way's spiral arms, passing through regions of varying stellar density and interstellar material. Over hundreds of millions of years, the Sun's path takes it through different neighborhoods of the galaxy, exposing the solar system to different levels of cosmic radiation, dust, and gravitational influences from nearby stars. These long-term cycles may have subtle effects on the Oort cloud, occasionally sending showers of comets toward the inner solar system. We are not stationary observers, but travelers through a dynamic, ever-changing cosmic landscape. Some scientific mysteries remain unsolved. The precise mechanism that heats the Sun's corona to temperatures far exceeding its surface is still debated. The true nature and origin of dark matter and dark energy, which dominate the universe, remain unknown. Whether Planet 9 exists in the outer solar system awaits confirmation. Whether life exists beneath the ice of Europa or Enceladus is a question we have not yet answered. The solar system, for all we have learned, still holds secrets in its shadows, puzzles in its orbits, and possibilities waiting to be discovered. Every object in the solar system tells a story. The cratered surface of Mercury speaks of billions of years of impacts. The backwards rotation of Venus hints at a violent collision, or slow tidal evolution. The Grand Canyon-sized scar on Mars whispers of ancient tectonic forces now silent. Jupiter's Great Red Spot testifies to storms that can rage for centuries. Saturn's rings shimmer as temporary guests in cosmic time. The geysers of Enceladus reveal hidden oceans beneath ice. Each world, each moon, each asteroid carries within it a fragment of the solar system's history, written in ice and rock and magnetic fields. The sun itself will not last forever. In about 5 billion years, it will exhaust the hydrogen fuel in its core and begin to change. It will swell into a red giant, expanding outward until it engulfs Mercury, Venus, and possibly Earth. The sun's outer layers will glow red and orange, casting an eerie light across whatever remains of the inner solar system. Eventually, it will shed these outer layers in a beautiful, glowing shell of gas called a planetary nebula. What remains will be a white dwarf, a dense, Earth-sized core made mostly of carbon and oxygen, no longer producing energy through fusion, but glowing with residual heat. This ember will cool slowly over trillions of years, fading gradually into darkness. It will be the sun's final form, a quiet end to a long stellar journey. But that ending is unimaginably far in the future. For now, the sun burns steadily, the planets orbit in their elliptical paths, and the moons trace their own smaller circles around their parent worlds. The solar system continues its ancient rhythms, a clockwork of gravity and motion that has persisted for billions of years and will persist for billions more. It is a system of exquisite balance, where every mass influences every other mass, where orbital resonances keep worlds in harmony, and where even chaos has patterns. The solar system is also a place of astonishing diversity. From the scorched plains of Mercury to the frigid nitrogen ices of Pluto, from the crushing pressures of Venus to the ethereal hydrogen clouds of Jupiter, from volcanic Io to the methane lakes of Titan, each world is unique. No two planets share the same combination of size, composition, atmosphere, and history. No two moons are alike. Even asteroids and comets show remarkable variety. Some are solid rock, others are loose rubble piles. Some are ancient and pristine, others have been battered and reshaped. This diversity is a testament to the complexity of the processes that formed and continue to shape the solar system. Water, in some form, appears to be surprisingly common. Earth has vast oceans on its surface. Mars once had flowing rivers and may still harbor underground reservoirs. Europa, Enceladus, Ganymede, and Callisto likely have subsurface oceans. Titan has a water ocean, while its surface holds lakes of methane. Even distant Pluto may hide liquid water beneath its frozen shell. Mercury and the Moon have ice in permanently shadowed craters. Comets are largely made of water ice. Water, the molecule essential for life as we know it, is woven throughout the solar system, hidden beneath surfaces, locked in ice, or flowing in alien forms. The search for life beyond Earth naturally focuses on these water-rich environments. Europa and Enceladus, with their subsurface oceans and possible hydrothermal vents, are among the most promising targets. Titan, with its complex organic chemistry and liquid cycle, offers another intriguing possibility. though life there would have to be fundamentally different from Earth life. Mars, with its history of water and possible subsurface liquid, remains a candidate. Future missions may drill through ice, sample plumes, or search Martian soil for signs of past or present microbial life. The question of whether we are alone is one of the deepest questions humanity can ask, and the answer may lie waiting beneath the ice of a distant moon. The solar system also serves as a laboratory for understanding planetary processes. By studying worlds with and without magnetic fields, with and without atmospheres, with and without tectonics, scientists can better understand what makes Earth habitable and what drives planetary evolution. Venus teaches us about runaway greenhouse effects. Mars shows us what happens when a planet loses its magnetic field and atmosphere. Jupiter reveals the behavior of gas giants. The moons demonstrate the effects of tidal heating. Each world is an experiment, a data point in the broader study of how planets and moons form, evolve, and change over billions of years. Technology has allowed us to explore these distant worlds in ways that would have seemed impossible just decades ago. Spacecraft have visited every planet in the solar system. Landers and rovers have touched the surfaces of the Moon, Mars, Venus, Titan, and asteroids. Orbiters circle Mars, Jupiter, and Saturn, sending back streams of data. Probes have plunged into Jupiter's atmosphere and sampled the plumes of Enceladus. Telescopes both on Earth and in space watch planets, moons, and asteroids continuously. Humanity's reach has extended across billions of kilometers, bringing distant worlds into focus and revealing their secrets. Yet for all this exploration, the solar system remains vast and largely unexplored. No spacecraft has visited Uranus or Neptune since Voyager 2's brief flybys in the 1980s. Most of the moons remain unseen except as points of light or low-resolution images. The Kuiper Belt and Oort cloud are almost entirely unknown. Even nearby objects like asteroids are just beginning to be studied in detail. There is so much left to discover, so many questions left to answer. The solar system will occupy explorers and scientists for generations to come. The solar system is also a place of profound beauty. The pale blue dot of Earth suspended in a sunbeam. The delicate arc of Saturn's rings catching the light. The swirling storms in Jupiter's clouds. The heart-shaped plain on Pluto's surface. The geysers of Enceladus spraying ice into space. The hexagon at Saturn's pole. The backwards orbiting moon circling Neptune. These are not just scientific facts, but images that inspire wonder, that remind us of the elegance and strangeness of the universe we inhabit. And perhaps most remarkable of all is that we are here to witness it. We are made of atoms forged in stars, standing on a planet that formed from the debris of the solar nebula, looking outward at sibling worlds born from the same cloud of gas and dust. We are part of the solar system, not separate observers but participants in its ongoing story. Our existence, our consciousness, our ability to wonder and explore, all emerge from the same processes that created planets and moons and stars. The solar system is not just a collection of objects orbiting the sun. It is a family of worlds, each with its own character and history, bound together by gravity and shared origin. It is a dynamic system, constantly changing on timescales from seconds to billions of years. It is a laboratory a source of wonder, a frontier for exploration. It is our cosmic neighborhood, the small corner of the universe we call home. As you drift now towards sleep, imagine yourself floating gently through this realm, past the sun's blazing surface and out through its corona, past Mercury's cratered plains and Venus's thick clouds, past Earth's blue oceans and the moon's ancient face, through the asteroid belt's scattered stones, around Jupiter's swirling storms and past its volcanic moon, through Saturn's glittering rings, and over Titan's methane seas, beyond Uranus rolling on its side, and Neptune's supersonic winds, out past Pluto and into the Kuiper Belt's frozen realm, and farther still, toward the edge where the solar wind fades and the stars grow brighter. The solar system is a place of silence punctuated by rare events. Most of the time, nothing happens. Planets orbit, moons circle, asteroids tumble slowly through empty space. The sun radiates steadily. It is a realm of patience, where change unfolds over millions or billions of years, where ice takes eons to sublimate, where craters remain undisturbed for geological ages, where the only sound is the hum of solar wind and the whisper of cosmic rays. In this quietness, there is peace. The solar system does not rush. It moves with the unhurried rhythm of celestial mechanics, following paths traced billions of years ago. There is no urgency here, no deadline, no anxiety. Just the slow ballet of gravity, the patient fusion of hydrogen, the gradual cooling of ancient heat. Time here is measured not in hours or days, but in orbits and eons. Let that quietness settle into you now. Let the slow spin of distant worlds calm your thoughts. Let the vast distances between planets create space in your mind. Let the ancient ice and patient rocks remind you that some things endure, unchanging, through spans of time beyond human comprehension. Your breath slows like the rotation of Venus. Your thoughts drift like particles in Saturn's rings. Your body grows heavy like the iron core of a planet, settled and still. The day's concerns fade like the sun's light at the edge of the heliosphere, growing dimmer and softer until they dissolve into the dark. You are floating now in the space between worlds, weightless and free, surrounded by the gentle presence of planets and moons and stars. The solar system holds you in its vast, patient embrace, a cosmic lullaby sung in the language of orbits and light. There is nowhere you need to be, nothing you need to do, just this quiet, drifting through the dark, this gentle floating through the realm of distant ice and ancient stone. The solar system continues its ancient dance around you, indifferent to human time, moving to rhythms older than memory. And you move with it, part of it, a small consciousness carried along in the great slow wheel of planets and stars, drifting now toward sleep, toward stillness, toward the quiet dark where thoughts dissolve in breath, becomes the only rhythm that matters. Let the solar system cradle you. Let the darkness between stars soften around you. Let the distant light of the sun become a memory of warmth as you drift farther out, farther in, deeper down into rest. The planets will still be there tomorrow, still circling, still patient, still waiting in the dark. For now, there is only this: the gentle pull of sleep, the quiet breathing, the slow dissolving of awareness into the vast, patient stillness of space. The solar system breathes with you now, in and out, the slow expansion and contraction of its boundaries as the solar wind waxes and wanes with the sun's 11-year cycle. Your heartbeat echoes the pulsing of magnetic fields, the gentle throb of tidal forces that knead the interiors of moons millions of kilometers away. You are connected to all of it, part of the same fabric of matter and energy that stretches from the sun's core to the edge of the Oort cloud. In the darkness behind your closed eyes, you might picture the solar system not as it appears in diagrams, flat and orderly, but as it truly is. A three-dimensional realm of spheres moving through emptiness, each world tilted at its own angle, each orbit slightly inclined to the others, creating a complex geometry that shifts and changes as the planets progress through their years. Mercury racing around the Sun in just 88 days, Venus taking 225, Earth completing its familiar annual circuit, Mars taking nearly twice as long, and farther out, the gas giants moving in stately procession, Jupiter's 12-year orbit, Saturn's 29 years, Uranus taking 84 years, Neptune requiring 164 years to complete a single revolution around the Sun. These are timescales beyond human life. Rhythms too slow to perceive directly. Neptune has not yet completed a full orbit since its discovery in 1846. Pluto, even slower, has not made a complete journey around the Sun since it was found in 1930. These worlds move with a patience that makes human urgency seem like the flutter of a hummingbird's wings, brief and inconsequential against the vast, slow turning of planetary time. And yet, for all their slowness, the planets are always moving. Right now, as you rest, Earth is carrying you through space at 30 kilometers per second. The Sun is pulling the entire solar system around the galaxy at 200 kilometers per second. The Milky Way itself is moving through the universe at hundreds of kilometers per second. You are in constant motion, traveling through space at speeds that would seem impossible, and yet you feel none of it. You rest, still and quiet, while the cosmos rushes past. This is the paradox of cosmic scale. We feel stationary, but we are moving. We feel solid, but we are mostly empty space. We feel separate from the stars, but we are made of star stuff, atoms forged in stellar furnaces, and scattered through space by ancient supernovae. We are not observers of the universe, but expressions of it, temporary patterns of matter and energy that have become aware of themselves, briefly, before dissolving back into the cosmic flow. The solar system itself is such a pattern, a temporary structure formed from a collapsing cloud of gas and dust 4.6 billion years ago. Before that, the matter that now makes up the Sun and planets was scattered through interstellar space. Before that, it was inside other stars, being fused and transformed. Before that, it was part of the primordial hydrogen and helium created in the Big Bang. The atoms in your body have been on a journey spanning the entire history of the universe, cycling through stars and nebulae and planets, and now, for a brief moment, they are arranged in the pattern that is you, aware and breathing and drifting towards sleep. Someday, billions of years from now, the solar system will end. The Sun will exhaust its fuel, swell, cool, and fade. The planets will spiral away or be engulfed. The moons will follow their parent worlds into whatever fate awaits them. The asteroids and comets will scatter. The matter that now circles the Sun in such orderly fashion will disperse back into the galaxy, available to be incorporated into new stars, new planets, new patterns yet to form. Nothing is permanent, not even planetary systems. Everything is in flux, slowly rearranging itself according to the patient laws of physics. But that ending is so far in the future that it is almost meaningless. For now, the solar system is young, stable, and full of mysteries waiting to be discovered. For now, the sun shines, the planets orbit, and life flourishes on at least one world. For now, there is this moment, this breath, this quiet floating in the darkness. Some facts are small and precise. The speed of light is exactly 299,792,458 meters per second. The mass of the sun is approximately 1.989 times 10 to the 30th power kilograms. Earth's orbital velocity is 29.78 kilometers per second. These numbers are exact, measurable, knowable. They give us the illusion of understanding, of control over the vastness. But other truths are larger and softer. The feeling of seeing Saturn's rings for the first time through a telescope. The awe that comes from realizing you are standing on a planet spinning through space. The quiet wonder of watching a meteor streak across the sky, a tiny piece of ancient solar system material burning up in Earth's atmosphere. The strange vertigo of understanding that down is simply the direction toward the center of mass, and that on the other side of the planet, people are standing upside down relative to you, held in place by the same gravity. These truths cannot be captured in numbers. They exist in the space between knowledge and feeling, in the sudden shifts of perspective that change how you see the universe. The solar system offers countless such moments. Learning that the sun's light takes 8 minutes to reach Earth means understanding that you never see the sun as it is now, only as it was 8 minutes ago. Realizing that when you look at Jupiter through binoculars, you are seeing light that left the planet between 30 and 50 minutes ago, depending on the relative positions of Earth and Jupiter in their orbits. Understanding that the light from Neptune takes over 4 hours to reach us, so that by the time you see it, the planet has moved, the moment has passed, and you are looking at history, not the present. This is true of everything you see. Light travels fast, but not infinitely fast, and so there is always a delay between event and observation. The universe you perceive is not the universe as it exists now, but a patchwork of different moments, stitched together by the varying travel times of light from different distances. The coffee cup on your nightstand is so close that the delay is immeasurably small. The moon is about 1 second in the past. The sun is 8 minutes ago. The nearest stars are years in the past. The distant galaxies are millions or billions of years old, showing us not what is, but what was. We live, always, in the past. The present is inaccessible, constantly receding ahead of us at the speed of light. This is not a limitation of our instruments or perception, but a fundamental feature of reality itself. There is no universal now, no cosmic clock that could synchronize all moments across the universe. Time itself is relative, flexible, dependent on motion and gravity in ways that defy common sense, but are nonetheless true. The solar system exists in a local bubble of synchronized time, at least approximately. The differences in time flow between the surface of the sun and the outer reaches of the Oort cloud are tiny, negligible for almost all purposes. We can speak of the solar system as it is now without significant error, from the inner world scorched by sunlight to the icy moons that whisper in the dark. We've wandered together through orbits, storms, and shadows, one sleepy fact at a time. If your eyes are already heavy, that's just fine. Let the last traces of starlight fade behind your thoughts, and let your breath carry you softly into rest. There's still so much more to discover, but for now you've learned enough. You've traveled far, and the universe can wait until morning. Thank you for spending this time with me. And so, under the quiet stars, the story continues. I hope you sleep well and dream softly. Good night.